Hello! In this video we are building our own custom e-ink dashboard, a neat device called Terminal, but written as TRMNL. No matter if weather forecasts, stock prices, news, it brings the world to your desk, but only the information you really care about. No ads, no blinking lights, no beeps. Just a calm, focused display of what really matters. If you've ever wanted a minimalist, ultra-low power display that fits perfectly on your desk or wall, you're in the right place. Let's find out how it works and build it from scratch, step by step, with the help of my AI assistant guiding you along the way.
Hey folks! Without further ado, let's dive in. A good starting point are the developer docs, especially the DIY terminal chapter. There, follow along with the BYOD section. BYOD stands for Build Your Own Device. To do so, we need an EPD screen like the 7.5-inch e-ink display from Waveshare. These are available from Amazon and many other marketplaces. I got mine from PCBWay, who are the sponsor of this project. In a nutshell, PCBWay is a one-stop solution for electronics hardware development and manufacturing. They handle PCB fabrication for just about any type of board, from standard PCBs for home appliances and hobby projects to advanced industrial-grade builds, including flexible boards. And if soldering isn't your thing, no worries. They'll assemble the boards and even source all the necessary components. They even have a module store. That's actually where I got the e-ink display. It supports 3 colors, black, white, and red. The current terminal firmware only supports black and white, but hey, maybe we'll put that red to use later. The display comes with a Raspberry Pi hat, but we want to use it with an ESP32 instead. No deal. Waveshare makes a universal e-paper panel driver for all its e-papers. And yep, you can get that from PCBWay too. A few days later, the e-paper screen arrived. And this is the Raspberry Pi header that came with it. But if you're not planning to use a Pi, you can also hook it up to any other SBC or microcontroller using the 9-pin edge connector. The breakout cable you need is included in the package. Since communication is handled over SPI, you're not locked into using any specific microcontroller. So the module is widely compatible. But with the e-paper driver board from Waveshare, it gets much simpler. Just connect it using the FPC cable. And that's it. The only thing left to do is load the terminal firmware onto the ESP32. Let's do that now. To build your firmware image, make sure you have the Visual Studio Code IDE along with the Platform I/O extension installed. You'll also need the Git command line tool. Once that's set up, head over to the Terminal GitHub repository and copy the repo link to the clipboard. Then open a command prompt and make sure you're in the parent directory that contains your Platform I/O project folders. There, type git clone, followed by the URL of the repository you just copied. Once the files have been downloaded, change into the project directory and type git checkout tags /v1.7.1. This command rolls the main branch back to a stable release, version 1.7.1 in this case. You can of course also download these versions as zip files if you prefer. When you start VS Code, Platform I/O will automatically detect and load the project. Click the ant icon to open Platform I/O Home, go to Projects, and find the new entry for your terminal build. Click Configure, and make sure to select the Waveshare ESP32 driver as the default. And don't forget to save. Initially, Platform I/O will automatically download and install all the required toolchains, SDKs, and libraries it needs. This can take quite a while, so resist the temptation to interrupt the process. Just let it finish.
One eternity later.
We're all set. The firmware is ready to be compiled and uploaded to the driver module. Before loading the firmware, connect pin 33 of the module to a push button that pulls 3.3 volts to ground when pressed. This button will be used later to flip through pages or reset terminal. After building and uploading the firmware, my 3-color display showed some odd behavior. I reported the issue in the GitHub repository, but so far, there hasn't been a response. Hopefully, by the time you replicate this project, the issue will be resolved. But if not, you can apply the fix I've shared in the GitHub issue. But like I said, you can skip this step if you're using the standard black and white only display, or if the issue has already been resolved in the latest firmware. Then compile and upload the firmware again, and congratulations! If you see this screen, the firmware is running. Now it's time to configure your device's Wi-Fi. Connect to the temporary network provided by the ESP32. This will open a captive portal page where you can enter your Wi-Fi credentials. If the portal doesn't open automatically, try entering the IP address 4.3.2.1 directly into your browser. Alright, as soon as you see this screen, it's time to register your terminal. To do that, you'll need a BYOD license, which you can order online. You'll usually get a confirmation email with your order number shortly after placing your request. With this order number, you can claim your friendly ID, which is required to register your device. Just enter this and an email address or nickname into the form, and you'll immediately receive a 6-character-long code. Use this to add the device to your account. I've already done this off camera, so now I'll just walk you through the settings you'll need for your new device. The first one is the device name. You can set it right here. Then set your device model. You see, there are many different e-paper devices compatible with Terminal, even jailbroken ebook readers. For my setup, the Terminal OG 2-bit is the best fit. It gives you not only black and white, but also 2 extra shades of gray. The next drop-down sets what Terminal should do when you press the button for more than 1 second. It links to a help page where all the options are explained. I'm not going to go through all of them to keep the video tight and focused. Feel free to pause here if you're curious and want to explore the options yourself. Under Battery and Sleep, you can optimize power usage. In sleep mode, the device stops refreshing for a set period. If you like, it can show a sleep screen during that time. Below that, you can adjust how often Terminal refreshes and displays new content, a setting that has a direct impact on battery life. Here you can choose between black and white and grayscale with 4 shades, depending on your personal preference. The firmware settings are not relevant here. OTA updates aren't supported for BYOD devices. And maximum compatibility has no effect since we disabled full refresh earlier when we applied the patch. With mirroring, you can share the content of your terminal with another device, so both show the same screen in sync. Finally, enter the MAC address displayed on your terminal into the MAC field under Developer Perks. Let's activate the terminal now. Press the device button, the one connected to pin 33, and terminal will restart with a prompt to register using your friendly ID. Press the button again, or reset the device to complete the registration. Terminal is now successfully set up and ready for plugins. But before we continue with that, I'll quickly build the display and electronics into a neat enclosure. So I designed one in FreeCAD and uploaded the exported step files to PCBWay, who also offers 3D printing services. As a material, I chose PETG, color is white. And here are the parts. Frodo, my furry assistant, is in charge of quality control, and he can't wait to inspect everything that just came in. Alright, all the quality checks are done, so it's time to start assembling. The FPC cable from the display feeds down into the bottom part, where the ESP32 and driver board will be installed later. Then I clamp the display into the recess, where it fits perfectly. I insert the back cover. The lower part is held in place by the housing itself, while the upper part is secured with 2 screws. So now we're ready to configure the plugins. Log into your terminal account and head to the dashboard. Click the Plugins button in the bottom row. This will take you to the plugin page where you can choose from over 700 available plugins. You can easily find what you're looking for by clicking on one of the keywords, or by entering one into the search field. Let's go ahead and install the plugin for local weather. With Tempest as a data provider, you can use your GPS coordinates or a station ID as the data source for local weather. Alternatively, you can select Weather API and simply enter the name of your location below. Then choose the units you're most familiar with. Click Save. Shortly after, you'll see a preview of what will appear on the e-paper screen, and terminal will update accordingly. Now you can optionally give it a name for reference and decide how often terminal should refresh the weather data. Save your settings again, and you're all set. You can add as many plugins as you like. On the dashboard, click on Edit Playlist, and you can adjust their settings just like we did earlier. You can also remove, hide, or reorder them, and set how long each one stays on screen individually. There can be as many plugins as you like in the playlist because they don't actually run on the ESP32. They're just 1 or 2-bit bitmap images hosted on a web server and simply displayed by terminal, kind of like static web pages. Native plugins are developed and maintained by the terminal team, while custom plugins are supplied by the community. These can be shared with other terminal users through so-called recipes. Anyone who owns a terminal can write and share their own, and the community is very active, with new recipes being published every day. You can add a recipe like any other plugin, but keep in mind that any changes made by its author will automatically affect your installation too. To avoid this, you can fork it, creating your own independent copy that you can freely modify. Like a website, plugins are written in HTML, CSS, Liquid, and server-side JavaScript. You can edit them right in the built-in online editor and instantly preview your changes in a separate browser window. Let's talk about the electronics now. On the driver module, you'll find 2 dip switches. Switch number 1 needs to be set based on the table shown in the module's wiki page. For 7.5-inch displays, it should be in position B. The other switch disconnects power from the USB serial converter with the intention to save battery life. However, the converter chip gets its power directly from the USB port. But when powered over the 5-volt pin like here, there's no difference between the 2 settings. So a switch for the red indicator LED would have made more sense here. If you want to run terminal from a lithium-ion battery, you'll need a charger module. This one includes a USB connector and protects the battery from overcharging and deep discharge. The 5-volt power pin of the ESP32 driver board accepts supply voltages from 3.6 to 5 volts, so it can be connected directly to the output of the charger module without any additional regulation. Since the battery voltage must stay above 3.6 volts, only about 80% of its capacity can be effectively used. The remaining 20% is inaccessible. Another issue is that the ESP32 draws short power peaks of up to 500 milliamps when communicating over Wi-Fi. These spikes can briefly pull its supply voltage far below the critical 2.5 volts, causing the ESP32 to reboot and get stuck in an eternal boot loop. This becomes increasingly problematic as the battery voltage gradually drops during discharge. A 1000 microfarad capacitor connected between the 3.3 volt pin and ground can help stabilize the supply voltage. You can also add these 2 lines of code into the main firmware file. They disable the brownout detector of the ESP32, an internal circuit that reboots the CPU when the supply voltage drops below 2.5 or 2.6 volts, depending on the revision. Disabling it lets us extend the operational voltage range a bit further. Additionally, you might consider adding one of these boost converter modules to make full use of the battery's capacity. However, these typically operate at a maximum efficiency of around 80%. You also need to take their standby current into account, so the actual benefit may be minimal or even negligible. And I have to warn you, although this module works best, it sometimes outputs more than 30 volts, which wrecked both my e-ink screen and the driver module, parts worth over $90, including tax and shipping.
No! God, please, no! No!
This was one of the moments when I hated this job, but making the AI effects was actually fun.
So we decided to move forward without the buck converter. Here's a simple hand-drawn sketch to show how all the components are connected. And here I've put it all together. The driver board and its external components are mounted on a piece of prototype board, which is screwed onto the standoffs on the bottom plate. The charger module fits perfectly into the recess in the corner, and by a handy coincidence, the battery fits exactly into the space beneath the prototype board. And since we're professionals, we secure it with hot glue. Same goes for the battery. I also spliced a switch into the battery leads, allowing us to disconnect it entirely when running on USB power only. If you decide to run it on battery, you might want to remove the power indicator LED. It constantly draws about 2 milliamps of current, an unnecessary drain that shortens battery life.
Alright, as a final step, mate the bottom part with the electronics and the shell, then secure everything with screws. And there we go. Don't forget to like the video, check out the others, subscribe and build your own terminal. See you next time.